happy to have with us today Ahmed Ghoniem, who is a colleague of David Wilson's and in the mechanical engineering department at MIT, which makes it a special occasion to have one of David's colleagues join us. And Ahmed's going to speak today about fossil fuels or fuels beyond fossil, why, when, and what. And Ahmed, it's good to see you. I'm delighted to have you with us today. So I'll turn the floor over to you. We have your screen up, so I think we're ready to begin.
Excellent, excellent. Thank you. Thank you very much, Ron, for the quick and short introduction. Makes it easy to take some time to introduce myself, but instead of introducing myself, I think I will do something different. I will acknowledge first a whole bunch of fantastic graduate students I've had over the years. I've been at MIT for 40 years now. 4 decades is a long time, but it's been fun, so I'm still with it. But one reason that I came and stayed at MIT is the graduate students that I've had the pleasure to work with, and I'm always happy to start by acknowledging them, but so many of them that I cannot mention their names. So I will show you pictures of them as we move forward as a way of acknowledging their contribution to what I know and what I have done. So this is a Winchester-Wilson seminar, and acknowledging Winchester as a town that my wife and I have lived in for about 40 years now since we got married. But I also want to start with reminiscing a bit about our great colleague, David Gordon Wilson. Many of you know him, but I have known him a bit closer in different forms. And I wanted to start by telling a few things about him and about my interactions with him during the period of time that he was with us. So I joined MIT in 1983, and his office was a floor above my office. And as you well know, he was a very friendly man. He always took the initiative of coming to introduce himself and say hello and tell me a bit about himself. And that's always great when you join a place. I was in UC Berkeley before, so I had just moved to the East Coast and Massachusetts and MIT, and obviously I was keen to meeting as many people as possible. I remember he was one of the first to come down and introduce himself and tell me a bit about himself. I like that so much. I kind of used him over the years as sort of an unofficial mentor, someone to go to, ask questions, and exchange some experience with. He was very generous, and he had a very kind of a light touch in being a mentor. He never really dispensed advice, but shared experiences. Turned out that he was also a collaborator. So when I started my career in the 80s, I was one of the early engineering scientists, I guess a better way of putting it, to do computing, to do advanced computing, high-performance computing, as we used to like to call it. And I was very much into mathematics and computing and so on. So there wasn't much of an intersection with him. He was more interested in gas turbines, as some of you might know. So in the 80s, we just talked, and in the 90s, I started expanding my research a bit to applying computing to propulsion, gas turbine, jet engine, rockets, and things of that sort. And that opened the door for actual interactions. And we did have more than one joint projects in the 90s working on using gas turbines for very environmentally focused concerns. You probably know now that there's a lot of concern about methane leak, because methane is a greenhouse gas. I had a project with David in the 90s about how to use methane leaking from mines in a productive way. And I was more interested in the burning of the methane, and he was more interested in suggesting what kind of gas turbine engine will be most compatible with it. And interestingly enough, we ended up buying is a strong word, acquiring an M1 tank engine that's used in the Bradley tank at the time was, I think, the most efficient gas turbine engine available. And we worked with a third party to test that engine. Later on in the 2000s, when I became more interested in energy, we did a bit of work on what's known now as solarized gas turbines that use solar energy directly. So as you can tell, I knew him more than just as a friend and a mentor, but also as a collaborator. He was a role model in the sense that he was always interested in the environmental aspects of what we do. He always raised that to a much higher level. And, you know, in the 80s and the 90s, probably that was not as highly taken very seriously, I should say, as it's been now. But learning from what he had done in merging things like solar energy and turbines, as well as his bicycle and his push for environmental policy, definitely left an impression on me when I started getting much more interested in energy technologies and low CO2 technologies and so on. I will finish my reminiscence about him by also saying that he was a man with a fantastic sense of humor that you can never forget. And I will tell you about an incident that Elizabeth, my wife, will also remember that shows his sense of humor in a very, very stark way. In the 90s, we had a department head in our department. He was an interesting man. He was a bit of a confrontational person, but for good reason. He did very well for the department, and he pushed us to go beyond our limit. But he was also very confrontational. David and Ellen, his wife, invited Elizabeth and I to their house for dinner, and here in Winchester. And I didn't know that. We went in, and the other dinner guest was the department head and his wife. His name was Namsu, by the way. So that's fine, great. I was happy to see that, but I also knew that there were some issues, some concerns that I had known about before. The dinner went well. After dinner, David decided that we needed to play a game.
No.
The game that David decided to play was each one of us should say what we are annoyed most with our partner or spouse. David insists that we take turns about saying what annoys us the most. You can imagine what the rest of the evening was like. Anyway, I think I've taken more time than I should, but I think David does deserve to be remembered, not only in the context of our seminar, but as a great colleague. So now let me start talking about what the topic is. And the topic is fossil fuels, and where are we going to go from there? What I like to talk about as fuels beyond fossil. And I will start this talk like many times when I start talks like these, or I start lectures at MIT, I start with a bit of either a story or a joke or a kind of a lighter version of the message. And I will do the same here. And I will say that when we talk about fuel beyond fossil, we talk about the transition. And we're currently talking a lot about transitions and energy transition. And if you step back and think about it, well, it's not the first time we do an energy transition. We have been doing energy transitions for the past 150, maybe more years. And I'd like to prove that to you before I start talking about fuels by showing you the change that we have lived through in transitioning, maybe in one application of energy, very important, which is transportation. So now we talk a lot about biomass, right? We talk about using biomass for fuel. Well, here it is in front of you, the original biomass utilization in transportation. A couple of donkeys pulling a cart. So that was the early use of biomass in transportation. Of course, later on, internal combustion engines were invented and fossil fuels became plentiful and cheap, and we all started driving cars in gasoline or diesel or a fuel like this. Well, in the 2000s, when the CO2 issue started to take center stage, companies started thinking maybe we should switch from burning fossil fuels to burning hydrogen, which is really one of the topics of today's talk. And several of them, including BMW, the one you see here down at the bottom of my screen, converted their engines to run on hydrogen and actually started selling cars in different places that ran on hydrogen. That was in the 2000s. In the meantime, given the fact that we don't have a hydrogen infrastructure, other companies started thinking, well, we should think about efficiency. We should be hybridizing our cars, like Honda and Toyota and Priuses and so on. Very few know, and I'm not going to take a quiz here, but very few know that the hybrid car was invented by no less than Porsche. The name associated with cars that many of you, many of us love to have. Turned out that Porsche invented the hybrid automobile in 1900, more than 100 years ago. And the picture you're seeing in front of you now is actually a Porsche designed hybrid car. In 1900, he was interested in racing. He was not interested in CO2 or efficiency. He was interested in how to develop the fastest possible automobile. Being a great engineer, he realized that motors accelerate faster than engines. And if he develops a hybrid car, he can race and win every race he can get in. Indeed, he did. Indeed, this monstrosity that you're looking at allowed him to win many races. Unfortunately, he was not able to sell many of them. It just did not look like a race car. Nevertheless, we must acknowledge his contribution to the hybrid powertrain. In fact, I should say that this hybrid car you're looking at here is more advanced than any hybrid car you can buy today. He was able to embed the electric motor in the wheel. This wheel here has an electric motor embedded in it. So he really had the hybrid car right. Again, it was not as practical and it did not survive. Fast forward many years, we had cars that run on biomass by gasifying biomass and pulling the biomass gasifier behind them. They became popular during World War II. Fast forward many years, you're looking at the Mirai, another hydrogen-driven car that Toyota sells in several places, including California, using a fuel cell and hydrogen. Fast forward, we get into the electric car. But of course, the electric car was the first car invented. Electric cars have been around since 1830s, 1840s, before the invention of the IC engine. And here is your electric car in 1984 and your electric car in 2019. What is the message here? The message here, we've had many transitions before, and technologies came and went, depending on the need, availability, scalability, price, regulations, and so on. We can talk a lot about the history of the cars, and I'm showing it here on the left-hand side of your screen from the 1830s till today's cars, but that's not really the subject of today. The subject of today is if we're going to continue to electrify like what we're doing now successfully in transportation, what could we be leaving out and why might we still need fuels? So we're talking about electrifying transportation, electrifying heating by heat pumps and so on. But what will still need fuels and why we will continue to need them, what kind of fuels we might use, and when we will make that transition. So with this introduction, I remind you of two more things that I think are important to remember when we're thinking about energy transition. How much energy we currently consume, in what form, and where it comes from. So believe it or not, till today, after all the effort that we've been put in, we still use fuels to produce 90% of our energy. Coal, oil, and gas come at the top. Next comes biomass, contributes about 10% of the energy worldwide. Then comes renewables and nuclear. What is the point here? The point here is fuels still play a very significant role in our energy production. Some of them are used to produce electricity that will likely be replaced with renewable and nuclear, but some of them are also used for transportation and other applications that we'll show in a second. So with the huge amount of energy we produce or we need to survive worldwide, and with 90% of them being fuel, we cannot completely, totally think that fuels will disappear. Closer to home, here is our own consumption in the US, about 1/6 of the total world consumption. 82% of that consumption is still fuels. Again, coal, gas, and oil, and biomass. Biomass still represents about 40% of our total renewable energy consumption. So we reduced our dependency on coal significantly over the past 15 years. That was replaced by the renewables and natural gas. But still, that contribution of fuel to our consumption is massive. All right. We will electrify and we will continue to move away from fuels by using electricity. Maybe electricity will not be produced by fuel, but maybe it will be produced by fuel. But there are sectors in the economy that will be extremely difficult to move away from fuel. By the way, we call this tough to electrify or tough to decarbonize because we're thinking about decarbonization as getting away from fossil fuels that produce the transportation fuels. So there are sectors in the economy that will continue to be tough to decarbonize or tough to move away from fuels. And I'm showing them here in this slide. With in the center, the toughest one to decarbonize, which what we will call long distance or long haul transportations. Transportation systems that move long distances without having access to refueling. Clearly, these are avionics, air transportation, ships that cross oceans, and long-haul trucks, the tractor trailers that have to go 1,000 and sometimes more than 1,000 miles in a single tank of fuel. Clearly, batteries are not going to be able to power these systems, and we'll show you some numbers soon. And we will need some other forms of fuels. We will call them either synthetic liquid fuels or liquefied hydrogen or other strange fuels like ammonia and so on to replace the existing fossil stock. The other sector is industrial heating. There are some industries that require very high temperature heat that will also be difficult to get away completely from fuels. There has been lots of effort, and the effort is ongoing to potentially electrify these industries as well, but still a lot feel that electrifying them completely may not be the most economical approach to it, and we need some fuels to power them. The last one, I know many of you have been interested in the grid, is long-term energy storage. Long-term energy storage is important because the renewables that we are likely to depend more and more on, like wind and solar, and intermittent. And we may need storage of electricity or of energy that go beyond days, maybe weeks, and even seasonal. These tough to decarbonize sectors currently emit somewhere between 15 to 20% of the total CO2 worldwide. Depends on how you count and where you draw the boundaries and so on. So whether it is transportation or industry or what we call load following electricity that responds to intermittency. And here we're showing some of these numbers. I apologize for showing too many numbers, as like many of you, I'm an engineer, and engineers work with numbers only. So it's very difficult to give a talk without throwing around all of these numbers. But they are our kind of our guardrails, if you like. We like to take them to justify what we do. So again, this slide is just meant to emphasize that the goal here is to decarbonize, and we need to look at sectors that will be tough to decarbonize using electricity and see how we can invent, if you like, new fuels, sustainable fuels that will replace those. So again, because of many of you I know and I've spoken to before are interested in the grid and how we're going to stabilize a grid that may rely more and more on intermittent sources like wind and solar. I will remind you that as wind and solar penetrates the grid more and more, to counter the intermittency, we will need storage beyond hours and even beyond days to sustain steady supply of electricity, and to prevent what we call curtailment, which is disconnect the renewable sources. So we need to have a way of storing that power being generated when we don't need it and store it in a way that we can use it over days, weeks, and months. And the further or the higher the percentage of renewable in our grid, the longer the storage time may be needed. The very last part of this plot, which shows what we call the seasonal, but even days and weeks, we're having batteries to support storage over weeks and seasons may turn out to be very expensive. All right, so I sort of assumed that you will all agree with me that flying on a battery is not possible. Flying a 747 on a battery, maybe flying a one-passenger plane is all right, but flying a 737 or 747. And again, sorry about it, but more numbers. Battery storage capacity, although it's improved enormously over the years, still very limited compared to how much chemical energy can be stored in a fuel. And even though the chemical energy converted from chemical energy to electricity or to power undergoes some reduction because of efficiency, still per unit mass of fuel, you can get 20 to 50 more times the power than you can get from a lithium-ion battery. So if you're concerned about the mass you're carrying or the volume you're carrying, there will be a limit to how big the battery you can put in if you are moving or transporting things over long distances, because the battery will grow and grow and grow to take you the distance, and the world range experience or range anxiety will take on a very different meaning. So the slide really shows where lithium-ion batteries stand versus something like hydrogen or liquid hydrogen in particular, in terms of the amount of energy per unit mass you can carry. And you know, I don't need to tell you more about it. Of course, it's never as simple as just one number, because you also have to worry about the energy per unit volume. Sometimes the volume is even more important. But even then, with liquid hydrogen or liquid synthetic fuel, you go much further. You can go on a battery. Especially when we think about the volumetric issues, how big the battery is volume-wise, which may be important in things like ships and planes. Again, liquefying the fuel or turning it from a liquid hydrogen, for instance, into something like methanol or ammonia will allow us to carry more energy per unit volume than we can ever be able to do in a battery. Now, some of you might have heard that ammonia is currently being considered as a fuel. Indeed, it is, with all the complexities associated with it, but ammonia carries a lot of hydrogen in it. Ammonia is very easy to liquefy and at temperature reasonable to ambient temperature, versus hydrogen, which needs much lower temperature. So although we never think of ammonia more than a fertilizer, it really is a fuel. And there's much need and much concern and much effort currently to look at how can we develop infrastructure as well as engines that can operate on ammonia. Methanol is another one of those as well. Again, sorry about the numbers, but we're in the same place still. If you want to appreciate the magnitude of the complexity of long-haul transportation, if you take aviation, shipping, and long-haul transportation, this is a $900 billion per year market. Let me repeat that: $900 billion dollars per year market. This is a massive market. Just to fly and to move across oceans and move long distances. So this is a market, just long distance transportation by itself, that cannot be ignored. And again, here, as one last attempt to make my point about the need for fuels, take a long-haul tractor trailer that moves across country. Believe it or not, the current range for tractor trailer is about 2,000 miles in a single fuel tank. Fuel tank is 300 gallons. If you're going to replace 300 gallons of diesel with batteries, it will be 6,000 gallon size. The weight of the diesel currently is about 1,000 kilogram. It will become 13,000 kilogram if it turns into batteries. If we replace it with hydrogen, it will be only 150 kilogram, about 1/10 of the weight of diesel, because hydrogen packs a lot more energy, and less than 1/100th of the weight of the battery. Of course, you know, volume is also important for long-haul trucks, because you want to carry goods instead of carrying fuel. So that's one example of why, and even the simplest one, which are trucks, will likely benefit greatly from switching to a fuel like hydrogen. And some of you may know that Toyota is already marketing a technology in that area. I can spend more time on shipping and on aviation, but just because time is starting to run out and I need to get into some of the technologies, I'm just going to say in passing that a typical ship, currently 10% of its weight is the fuel. If we're going to increase that by a factor of 10, we're out of the game. Nothing can be done. For planes, for big planes, 30% of the weight taking off is the weight of the fuel. So again, we cannot increase that by a factor of 3. It's just not going to work. A plane will need a fuel. It will need most likely liquid fuel, preferably synthetic liquid hydrocarbon fuel, in order to remain practical. So, answer, well, the current consensus is that hydrogen and its carriers and biofuels will be the replacement. Either you can use hydrogen as is, or you can use it as a part of a larger molecule, like methanol and ammonia. Or you can combine hydrogen with CO2 and form a synthetic hydrocarbon. Well, that's fantastic, but hydrogen is not a fuel. Hydrogen is what we call an energy carrier. We need to produce hydrogen. It's not like we can drill a hole, although there's some evidence that might be the case, that there's some wells that may have hydrogen in them, but that's still very, very speculative and very early. For now, hydrogen has to be produced by some technology. Breaking up water, H2O, will give us hydrogen. Breaking up methane, CH4, will give us hydrogen. Or using heat or electricity from other sources can do either of those for us. As I said before, you can combine hydrogen with CO2 to produce liquid fuels. That's a well-known technology. It's off the shelf. And you can combine hydrogen with nitrogen to produce ammonia. That's a very well technology. This was known as the Haber-Bosch process that we use to produce ammonia for fertilization. The other class of fuel that's very important are biofuels. And biofuels are currently being produced by fermenting fruits or grains. When you go to your gas station, you put gasoline that has 10% ethanol. The ethanol is produced by fermenting corn. And when you go to your wine store, you buy wine that has a lot of ethanol in it. That is produced by fermenting grapes. So remember, next time you drink wine, you are drinking fuel. You can set yourself on fire. Careful. But there's also another source of biofuels, which is known as lignocellulosic, which is the rest of the plant can be converted also to fuel by several means. Some of them are again, very much off-the-shelf technology, like gasification and anaerobic digestion or hydrolysis. All of these are ways to produce biofuels from lignocellulosic material from the plant. I did mention the Mirai before. Mirai is a Toyota that kind of looks like the Prius, but it does operate on a fuel cell with a hydrogen tank. The hydrogen tank in the Mirai has somewhere about 7 to 8, I don't know exactly what the latest figure is, of hydrogen. That goes the range of a battery that's about 500 kilograms. So the reason why Toyota believes that this should be part of the conversation is because, again, the total size and the mass of fuel storage is small, and hence range issues may not be as important. Now let's talk about hydrogen production. And many of us recently have been using what's become known as the color wheel of hydrogen. It's an interesting issue, because it turns out there are many ways of producing hydrogen. You hear a lot about green hydrogen. Whenever you hear about green hydrogen, it is basically produced by renewable electricity. Renewable electricity and an electrolyzer will produce hydrogen. But there's also gray hydrogen. Gray hydrogen is what's being currently produced extensively. That's produced from reforming methane. So if you take methane and react it with water, you produce a lot of hydrogen. But of course, you produce CO2. So that's why we call it gray. If you sequester CO2, it becomes known as blue hydrogen. So blue hydrogen starts in methane, but reforming methane and sequestering CO2 is a way of making it blue instead of gray, making it more environmentally friendly. There's also what's known as turquoise hydrogen. Turquoise hydrogen is just simply breaking down the molecule, methane molecule, into carbon and hydrogen by heating it to very high temperature. There's also a reddish type of hydrogen that's produced by electrolysis using nuclear energy. And lately, people have been talking about white hydrogen. White hydrogen apparently is what you can dig a hole in the ground and recover it. There is evidence that there are some underground deposits that have hydrogen in them. And there's been some experiment that shows that indeed the case in some places around the world, but this is very early in the discussion. So there are many ways of getting hydrogen. Some of them have some CO2, some of them don't, some of them sequester CO2, some of them get carbon out, and there's kind of the jury is still out, so to speak, on where all of these will go. I'm sure you heard about some of them before. Some of them use electrolysis, electricity from the sun to break water molecule, or photon from the sun, what's known as photoelectric or photoelectrochemical or photoelectrodes. And some of them use heat, just the heat from the sun. The two most advanced are the electrolysis that use electricity from the sun, and thermochemical, which use heat from the sun instead of electricity to break up water molecules. And I will say a bit more about those in a couple of minutes. Before I do that, I will say that I focus on these two because they are currently the most economical. There are lots and lots of techno-economic studies in the literature that compare the prices among these approaches that largely show that electrolysis and thermochemical are currently the cheapest in the sort of the green category, and the category that does not use fossil fuels. So in that sense, they are the most promising. In electrolysis, we just get electricity from the sun, put it through a device that is the inverse of a fuel cell to break hydrogen into oxygen and hydrogen. It's a very mature technology. It's been around for more than 100 years. Been a lot of improvements in it over the years, but this is a very traditional technology. Just to show you how much interest there is in hydrogen produced in general, but perhaps electrolysis in particular, this is a graph I took from a recent study that show or compare the operating hydrogen plants versus the ones under construction versus ones for advanced planning, early planning, and announced. And you can see that there's likely to be an exponential growth if all of this happens over the next few years in hydrogen production. Electrolysis, as I said before, is pretty mature. So it's almost off-the-shelf technology, although they come in different flavors and different variety. And many companies have started looking at the scaling of these electrolyzers to provide hydrogen at scale. I did mention before that hydrogen by itself may or may not do, because liquid fuels, liquid hydrocarbons, pack a lot more energy per unit mass and per unit volume. And this diagram kind of shows you a very futuristic way of thinking about what might happen, not only on Earth, but also on Mars. As you know, there's been discussions on colonizing Mars and going up and coming back down. And there's been effort to see how we can take advantage of the Mars atmosphere to produce fuels. Mars atmosphere is dominated by CO2. And there's been successful development of electrolyzers that can take CO2 and break it down to CO and oxygen. So it gives oxygen for people to breathe, and if CO as a fuel, because CO is a fuel. So MOXIE, the one that you're showing down here, is a real system that has operated on Mars and proven successful using an electrolyzer to break up CO2 into oxygen and CO. On Earth, there's been a lot of effort in not only taking water and getting hydrogen from it, but also taking captured CO2, combining the captured CO2 and water, or the hydrogen from water and the CO from captured CO2 to get CO and hydrogen, and putting them into different catalytic reactors to produce things like either liquid fuels or methane. So again, this is not happening now, but this is very much in the realm of technology that we can use. I will just divert for just 1 second to talk about biofuels. Biofuels are largely produced, as I said before, either by fermenting fruits and grains. This is not thought of as sustainable because fruits and grains take a lot of water, chemicals, and land to produce. But the more promising one is the one that will use the lignocellulosic component of biomass. And again, largely, this is a technology that is available. It has not been scaled, but it's available to be used to produce liquid fuels. And in the introductory remarks, I said that I had a project in my lab for producing solid fuels from biomass that was developed by one of my graduate students, Kevin Kong, who started a company called Takachar, and they have been competing well in producing these reactors in the marketplace and testing them and turning them into standard technology. But let me go back to hydrogen and hopefully wrap up in a few more minutes. Currently, hydrogen is very expensive, unfortunately, especially green hydrogen. Typical 1 kilogram of green hydrogen currently costs somewhere between $4 to $8 per kilogram. That comparing with less than $1 a kilogram of gasoline is expensive. The hope is that in 20, 30, 40 years, we'll be able to reduce the cost by a factor of 2 to 3. In fact, many of the current initiatives are intended to do exactly that. The target is $1 per kilogram, maybe by 2050, maybe $2 per kilogram by 2030. So that's about 1/2 or 1/3 of the current prices by continuing to improve the existing technology as well as exploring alternatives. Some of you might know that in the Inflation Reduction Act, there is a incentive of up to about, if I remember correctly, about $3 per kilogram of hydrogen to make even current generation of hydrogen production technologies somewhat competitive. Of course, we want to work towards technologies that will not rely as much on incentives. As one example, and now I get to my own research, work that's happening currently in my own lab, I have become interested in alternative to electrolysis. So instead of using electricity from solar PVs to break up hydrogen through electrolysis, become interested in using heat from the sun to break up water. And I become interested in it, not out of the blues, but because there's been several efforts in Europe in particular to advance this technology. And there has been several demonstrations, early demonstration that this technology does have the potential of getting us to the cheap hydrogen we would like to get to. In fact, this technology has an added advantage that it can work on both water splitting to produce hydrogen and CO2 splitting to produce CO at the same time, and produce a stream of gas, which is hydrogen plus CO, that can be converted to liquid in a catalytic reactor. This is a demo that was done in Spain about 4 years ago. This is a demo that's currently being done in Switzerland. And it's actually ongoing work that we're watching very keenly. The idea behind it is rather simple. We all know that metals tend to rust. If you put a metal in water, take iron will rust. Why does it rust? It grabs oxygen from water and turns into metal oxide and releases the hydrogen. So that is the essence of this technology, that we want a metal that can grab oxygen from water quickly, releases the hydrogen as a product of the process. To make it quick, we need to raise the temperature. We need to run this system at high temperature to make the chemistry move faster. But once you rust the metal, you're not going to dispose of it. You want to de-rust it. You want to remove the oxygen from it. To remove the oxygen from it, we move it even to higher temperature. We heat it even further up to release the oxygen from it, turn it back into a metal again, and take that metal that we release the oxygen from and react it with water to get more hydrogen. It's known as a redox cycle, a reduction oxidation cycle, or a looping technology where we loop between high temperature to release oxygen and low temperature to rust the metal again and produce hydrogen. This technology has a very high theoretical efficiency, about 70%, and work in my group has shown that we can build practical system and get about 40% efficiency. And it's a complicated diagram for demonstrating why it should work. Shows that there is one side, there's a very high temperature side that releases oxygen, and a low temperature side that reacts with water to produce hydrogen. And what we've worked on is what I would call the critical engineering for the system to make it efficient. How do we make it efficient? When you take heat from the sun at high temperature to release oxygen, you want to keep as much of this heat that you paid so much to collect, while you're dropping the temperature from the 1500 to the 900 to produce water. If you just dump this heat, the efficiency goes down to very low value, like 5%. If you take this heat and recycle it within your system, keep it within the system so that you can use it again and again, you can bring up the efficiency from 5% to about 40%. And that's what we designed in my group recently. So we think that by engineering the system better, we can improve that efficiency by a factor of 5, 6, 7, and that will get us to the cost we think will be compatible. So that's another way of looking at this system, that we will have collector concentrator of solar energy that will heat our reactor to release oxygen. Reactor will be cooled and react with water to produce hydrogen, get reheated internally again to go to the other side where we release the oxygen and loop again. I happen to have visited places in Spain where some of these experiments were run, and have seen in reality similar system that we would like to duplicate, but implemented on the design that we've come up recently. With that, I'd like to wrap up again and acknowledge again some of my brilliant students that helped make many of these things happen, and keep reminding me that remember to look at the stars, not down at your feet when you're thinking of new technology.
Thank you very much. That was just a remarkably comprehensive and really a brilliant presentation. I thank you for that. I do want to open the floor up to questions, but I'm going to lead off with a question and an observation and a question. Well, start with a question. Were the early hydrogen-powered automobiles, were they fuel cells or internal combustion engines?
The BMW was an internal combustion engine. The BMW that I showed was actually a traditional internal combustion engine that was modified to run on hydrogen by changing the fuel injectors and reprogramming the operation. One reason why it was sort of abandoned is fuel cells are just simply more efficient. If we replace the hydrogen engine with a fuel cell, we get more efficiency.
Yeah.
It's more expensive. Fuel cells are more expensive, but if you think about the long-term utilization, fuels usually play a long role in sort of the cost of operation.
Right. So, but I mean, I'm thinking about your comment about hydrogen is not a fuel; it's an energy source. In an internal combustion engine, it would be serving as a fuel, would it not? And that's it. I mean, this is semantics, I suppose, but just okay.
Absolutely. Technically, people have decided that we need to distinguish between what we call a fuel and an energy carrier.
Yeah.
A fuel
really in a
is
fuel
when
cell,
you
that's what you're looking at,
dig
right?
a hole in the ground and the fuel comes up.
Yeah, gotcha.
An energy carrier is something you have to produce.
Yeah.
It's not available naturally. And hydrogen, so far, we don't see it as being available naturally. We have to produce by using other energy sources and technologies.
Yeah. Now, the follow-up to this is that earlier this year, I think it was this year, maybe last year, we had a talk from Eric Miller, who is with the Department of Energy, and he spoke about a project called Hydrogen. You're probably aware of this.
I am part of it.
You what?
I am part of it.
Oh, okay. Well, then you know all about it. All right. So they're putting a lot of effort into water splitting, searching for stable semiconductor photoelectrodes for water splitting. Of all of the mechanisms for producing hydrogen, wouldn't you think that using sunlight and a semiconductor photoelectrode would by far be the least costly of all of the technologies that would be available or imagined?
if the catalyst is cheap
Yep.
and survives over a long period of time, the answer is yes.
Durable, right?
Exactly.
Yep.
So the key two words here is price and durability,
Right.
or your price and stability. So what has been challenging in the photoelectrode business has been getting away from rare earth metals or precious metals
Yeah.
into cheaper metals,
Yeah.
and making them survive long-term use,
Yeah.
operating efficiently and continuously.
Yeah.
To do this. So let me just add 2 points to this, because again, that's something I'm very much into. I don't do photoelectrodes myself, but I'm part of that big hydrogen
Yeah.
initiative.
Mhm.
The price is very important because we need to get to these targets that the DOE has set in. So when the price is important, you try to get away from precious metal as much as you can, if you can, as expensive metals, and you try to get systems that will survive many years in operation. You also want to use systems that can operate 24/7. That's another critical element. If you go buy an electrolyzer that uses solar PV, okay, if you just have a solar PV on top of your house and you go out and buy an electrolyzer to get you hydrogen, you will be able to operate that system 7-8 hours a day when the sun is out. And you will not be able to use it beyond that because storing electricity is very expensive. That means that the capital, the CapEx on your project will sit idle for 2/3 of the time.
Mhm.
That contributes non-trivially to the price of the hydrogen produced. You would like to have a system that can operate hopefully 24 hours a day continuously.
Sure.
If you can store the energy, that is possible. And we think that systems that use heat or thermal energy have a better chance of satisfying this requirement because storing heat is very cheap, much cheaper than storing electricity.
Yeah.
So if your system is using heat and you can store this heat in 5 bricks or some cheap element, you can use your hydrogen production system 24/7.
Gotcha. Good point. Let's take some other questions. Folks, any questions from the crew? No questions from this crew. That doesn't sound possible. Gunther, go ahead. Thank you.
Ahmed, thank you. This was very enlightening, I would say. And I hope that we get to hydrogen faster than your timeline. And it will probably depend on what you and your lab are doing. So I was wondering about your reactor that cycles between low and high temperature. How do you actually remove the gas from the reactor? So the oxygen on one end and the hydrogen on the other end.
Well, good to see you, Gunther. I see that you all recovered and looking healthy. That's great. That's a great question. So the way that happens is that you run steam through your reactor. You run evaporated water through the reactor. The reactor basically can hardly split all the water that you're running through, will only split a percentage of it, 30-40% of it, depending on the size, amount of metal that you put in it, and so on. So you put steam in, what comes out is a mixture of leftover steam and hydrogen, and you take that out, condense the steam, and get the hydrogen out. So by dropping the temperature, you condense the water that's left. You're left with pure hydrogen. Then you can take that leftover water and heat it again to convert it into steam. So that is how we separate or we produce the pure hydrogen coming out. Remember that the oxygen stays with the metal, so that's not the problem. The oxygen gets into the metal and makes it a metal oxide, and what comes out of the reactor is just the mixture of water and hydrogen. I should say, because it's something we're working on, that condensing is not the most efficient thing to do, because when you condense, you throw out heat. There are other technologies that will use membranes, for instance, a membrane that can pass one molecule, which is hydrogen, and leave steam behind it, so you can recycle the steam without cooling it. But this is still a technology in development.
Very good. Eddie?
Yes, I understand there's work we're utilizing photosynthesis to produce hydrogen. What is the status of that? Do you know?
Yeah, that's a good question. This is where you get, and again, I'm not the expert on it, so what I'm going to say is a very high level answer. My understanding is that the cost has been an issue. In one of my slides, I show the comparison among different technologies from the techno-economic point of view, and it shows that the photosynthesis is still very expensive. And largely, I understand it's because of the rare earth metals that they have to use to make it happen.
Tom?
Yeah, I was wondering if you can address quickly, what's the state of sort of large-scale transport and storage of hydrogen? So if you're going to make what's called gas stations, you have to get the hydrogen there and then store it for easy delivery. So what's the status of that?
Yeah, that's a very good question. And I should start by saying that when we talk about the production cost, $4 to $8 a kilogram, believe it or not, that actually pales compared to transportation and storage. By the time you do the transportation and storage using existing infrastructure, the price goes up to $16, $17, $18. Because hydrogen is a very light molecule, right? Very light gas. And you have to either compress it to somewhere between 300 to 700 atmosphere to pressurize it and get good volumetric efficiency, or liquefy it. Liquefaction is problematic currently because liquefaction uses a lot of energy. It's a refrigeration process. You have to go down to very, very low temperatures to turn hydrogen into liquid, close to the zero absolute. I mean, really ridiculously low temperature. And that takes a lot of energy. And of course, you have to put it in insulated tanks and things. So for small quantities, you may be able to get away with it without hurting the system too much. But for large quantities, it's still problematic. So the status is high pressure storage and transport is available, between 300-400 bar and 700 bar, whether you put it in tanks or mostly in tanks. I mean, I think the pipeline issue is still under debate because hydrogen tends to embrittle metals and react with metals in ways that may not be very, very, effective. So storage in tanks and transport in tanks is currently a bit more viable, whether in ships or tractor trailers. The liquid has the advantage of being twice as dense, so you get a bit more energy in the tank when you liquefy. You pay a bit more in terms of high energy penalty, but that will all come down to whether the price of the energy is higher or the price of the tanks that you use is higher.
Let's see. Pete, you had your hand up first, then we'll go to Avi.
Yes, I'm fundamentally a compressor guy. I spent 50 years in the business. I know how to make hydrogen and I know how to use it. I don't know how you get it from A to B. And it's all these issues that were alluded to moments ago. At one point in my life, I was a program manager temporarily for a Stirling engine. Hydrogen was the working fluid. We couldn't keep it in the machine. We had to have an onboard electrolyzer to keep the machine serviced. I think where it ends up is if you can make hydrogen at the point of use, whether it's a big power plant on the river using electrolyzed water, or if you're going to have a return to base kind of operation like a taxi fleet or something like that, where you can make hydrogen locally from natural gas, perhaps. 700 bar is scary for me. 10,000 pounds sitting under the passengers in the back seat of the car, I'm not comfortable with that. And at one point in my life, I worked with a company developing sensors for hydrogen tanks. It was a kind of a mesh that had sensors around it, and it was an attempt to look at failure mechanisms on the tank. But for me, it was the opportunity to do a life cycle tracing of hydrogen tanks, because after the vehicle is put out of service, the tanks will be repurposed. So you have to have some way to manage 10,000 pounds per square inch tanks. I think that's a fundamental flaw in the use of hydrogen for vehicles. Anyway, that's fine.
So you're not going to buy a Mirai then, huh?
No, I'm still driving my gasoline-powered M3
So the
BMW.
Mirai actually does have a 700 bar tank.
Yeah, I know they do.
Yeah.
Yeah, I don't want to
And,
buy one.
You know, just to add a little perspective on this, if you're interested in the materials of construction of hypersonic vehicles, as in the Space Force, the Air and Space Force, the fuel is hydrogen. And you're flying that thing at hypersonic speeds. So it can be done, Pete. But I take your point.
The space shuttle flew on liquid hydrogen. So, I mean, I think, Peter, let me give two responses. One is it's all engineering problems, and we love engineering problems, right? It's all in the engineering. There's no
scaling problem.
Oh, right. But as soon as we get it right, it can scale if somebody is willing to pay for it, right?
Yeah.
But that is exactly the reason why hydrogen carriers may be a better solution.
Yes.
The hydrogen carrier is a molecule that has lots of hydrogen in it that you can, on location, break it up and get the hydrogen out of it.
Yeah.
And the two examples for that are methanol and ammonia.
That would be the point source use, and how you get it from A to B is the issue. And so, but
I think Pete is raising an important point, particularly from the perspective of technology that's being introduced into a social device. The public is going to be, it's sort of like nuclear waste, no one wants it in their backyard. Will anyone really want high pressure hydrogen under their driver's seat? Those are the kinds of things we've got to deal with as technology evolves. And
at one point in my life, I was working on microturbines with Northern Research, and we were the first ones to do a solid oxide gas turbine hybrid at UC Irvine, 53% net electric efficiency in the 90s. But what I think, and you can run them backwards, I guess. I think what might happen is that we run those babies on natural gas where we got pipelines and use the SOFCE to make hydrogen locally.
Yeah.
And then you can use the hydrogen without the transportation issues.
Sure.
Problem
Yeah,
with that, by the way, is the SOFSCs require a turbine because they like low pressure.
Right.
And so what happens is they're not any gas turbines of scale at that low pressure ratio. So you're kind of limited to point of use and taxi locations and mail trucks.
Ahmed, we're almost at noon. Can you take 2 more questions?
Sure, yeah, no
Okay,
problem.
let's go to, good, thanks. Avi.
Well, it's really a little follow-up on what I've been hearing, but I'm wondering if you envisioning sort of broad-scale use of the hydrogen, is there any danger of the safety consideration of hydrogen can be very explosive?
Can't
And
see it.
it's not going to take much if one of these, something happens to scare the public away from ever using it. I mean, I guess the Hindenburg comes to mind, and it's nearly a century ago. So is that a concern in the broad scale?
Yes, big time.
Yeah, absolutely a concern, but not insurmountable. By the way, I don't know how many of you know that what triggered the fire in the Hindenburg was not the hydrogen. It was the casing of the airship. So just next time you think about the Hindenburg, Google the accident, and you find lots of reports about how the fire was triggered.
Okay.
So I can give you 2 answers, a lawyerly answer. On one hand, it is true that hydrogen is very explosive, is very flammable at low concentration. On the other hand, hydrogen is also very light, and when it gets released, it moves away from you very quickly.
Yep.
So unless you are in a very confined environment, the likelihood of explosion is not high. And I'm not, I'm not saying engineering problems in tongue in cheek. We live with many dangerous things around us. People forget that we live. I mean, lithium-ion batteries burn like mad, right? We've all seen lithium-ion batteries burn, and they're pretty dangerous. But with proper engineering, we learned how to harness them, and we learned how to minimize the risk. So it's a question of, agreeing what would be the best engineering solution to that problem if we want to deploy this technology at scale. Whether it will be a carrier, and on location you will break down these molecules and get the hydrogen out of them, or will be a very well-engineered system that minimizes, but it will never make the risk zero, but it can minimize it.
Yeah. Michael, you're going to have the last question.
Just quickly, thank you very much for this presentation, sir. I would say that the area that I am most interested in was the lignocellulosic fuels. And we're able to convert lignin and wood cellulose into not only gaseous high hydrogen content fuel, but also oils that can be used directly where diesel 6 can be used. So we not only rid waste streams, and I'm very interested in ocean-based biomass. There's enormous amounts of it available to produce liquids and gases while at the same time sequestering CO2 from the atmosphere. And that's the big difference between us and Kevin over at Takachai. He's doing great things, but he's not storing the oils and the gases. There's much heat going into the atmosphere with that particular system. So we capture all of that, and I think there's a great future there. And certainly welcome to take a peek. But after hearing it all and hearing the comments about hydrogen, metal embrittlement, pressure, transportation issues, my money's on lignocellulose-based biochar. Thank you very
Can
much.
it scale? Can it scale?
We can scale it, absolutely, very scalable.
Yeah, and I'm as I said before, right? That has been part of my research portfolio for a while, converting lignocellulosic to useful fuels. I would say that definitely there's tons of room for lignocellulosic biomass to be used for fuels. in the aviation industry, especially in the US, is now thinking about what's known as the SAF, Sustainable Aviation Fuel. And sustainable aviation fuel is all produced from lignocellulosic biomass. So the aviation industry, because they will have to rely on high energy density fuels, hydrocarbons, are betting definitely on biomass. Europe and Airbus is not as much. They're still thinking about hydrogen and synthetic fuel, what's known as e-fuel, synthetic fuel produced from hydrogen and CO2. The big limitation, as you know, is the supply. You know, how much lignocellulosic material can we get? The belief is that for aviation we probably have enough, but when you go outside that sector, then there's question marks about whether we will have enough lignocellulosic feedstock to produce the amount of fuel needed in the future.
I would agree with that, and I would say that's why we need to include waste streams, but I'm going to close my comment by saying this also. Perhaps hydrogen's best short-term use is to inject it into the fuels of ICE engines, where 4% hydrogen can increase the efficiency of that engine considerably, while cleaning up some of the toxic outputs or undesirable outputs. Would you comment on that just for a moment?
Yeah, so
hydrogen.
I would very, very quickly, because we're running out of time, but that is true. There was, for a while, a lot of interest was become known as the hythane, the mixture of hydrogen and methane for IC engines and other application. Unfortunately, and I say it unfortunately, the drive now is very quickly to green everything, to try to get away from the fossil sources as soon as we can, and to develop technology that will use renewables, whether it's the biomass or the sun or the wind and so on. So the sort of the blended solution, if you like, that can help in the transition, for some reason are not taking center stage at this point, but there's definitely room for blended fuels.
Oh, I disagree. The EPA's new standard is to mix hydrogen with natural gas as a fuel, and over a period of time go to 100%. So
okay, so they're buying into it. Good.
Yeah, they are.
Well, Ahmed, you can see that you've stimulated a lot of conversation and a lot of thought, and we all thank you for that. I'm just delighted that you were here with us today. I know that David would have been happy with this conversation too. So you've served a lot of purposes. One of the things you started out with was mentioning how proud you are of your students. I understand that. That's one of the things I treasure most about having been an academic, is to watch the growth of the students who are part of my extended family. Absolutely. And I mention this because when we meet again on December 22nd, we're going to hear from the Dean of Engineering at Tel Aviv University in Israel. It turns out that Noam Elias is a former postdoctoral student of mine at MIT. And I'll tell you, I'm very, very proud of this young man. So I'm looking forward to introducing him to all of you on December 22nd.